So, okay,
Yeah,
so we can
yeah,
start, right?
Yeah, we can
yeah,
start.
yeah. I'm ready to start.
Okay. So,
Yeah,
good evening, everyone. So, we are going to start our first lecture of Mathematics Online Seminar Series 2023. And today we have with us Professor Anirban Mukhopadhyay from IMSC. So, now I would request Kasi sir to introduce our today's speaker.
yeah. So, good evening, everybody. Welcome to this mathematics online seminar. This is organized by the team called Project Spiral. So, it's a great pleasure to have Professor Anirban Mukhopadhyay with us today. And he's a faculty member at Institute of Mathematical Sciences, Chennai. So, he completed his PhD from HRI Allahabad under the supervision of Professor S.D. Adhikari. And after that, he was a postdoctoral fellow at Institute of Mathematical Sciences, Chennai. And today he is going to speak on beyond uniform distribution. You can start, sir.
Thank you, Kashi. Uh, so, this my this where I'm going to write is visible to everyone, right?
Yes, sir, it's visible.
Yeah, and the thing is that you can ask question whenever you wish, but talk a bit loud because my the laptop speaker is very bad, and I don't want to put an earphone because it's quite hot. So let me start. So I presume that everyone knows uniform distribution, though I'm going to recall. So we would actually be talking about something finer than uniform distribution, and that's why I'm calling it beyond uniform distribution. So let's start by defining uniform distribution. So let's look at a sequence of real numbers. So it's a sequence. You can write it like this. So if you write it like that, then this is inside the 0, 1 interval. So we would always take 0 closed, 1 open, and also identify this with R mod Z. So you are essentially wrapping the real line around a unit circle. So all these are same. It's also the S1. It's also the circle. So everything is just same. Same in many ways, actually. So let's define what is uniform distribution. So if for all, so if for all sub intervals, so I'm going to write sub intervals like a comma a and b. So let's take a and b like this. So then as you can see that a comma b is going to be a sub interval of this 0, 1. So if for all of this we count the number of elements of the sequence up to certain capital N, which are inside this interval. So as I said, I will always take left closed and right open intervals. So we count the number of elements of the sequence till the first capital Nth element, which falls inside this interval, and then divide it by the number of elements so far we have looked at, which is capital N. And we expect that this quantity is equal to the length of the interval. Length of the interval, so A, B, which is of course nothing but just B minus A. And if this happens for all possible intervals, then we call that the sequence is uniformly distributed. And limit is of course taken as capital N tends to infinity. So if the limit exists and it goes to b minus a, then xn is said to be uniformly distributed. Uniformly distributed. So now, do I need to look at always sequences which are sitting inside 0, 1? No. We can look at other sequences of real numbers and then just look at the fractional part. So in fact, the first example is going to be like that. So we look at this sequence. So let alpha be a real number. Let alpha be a real number. Look at this sequence, alpha, 2 alpha, 3 alpha, all the positive integer multiples. You can also take negative integral multiples together, doesn't matter, but let's just keep to the positive side. So all the multiples. So that's a sequence of real numbers, not necessarily inside 0, 1, and of course they will not, all of them cannot be inside 0, 1. Whatever alpha, it's a fixed alpha, so whatever alpha be, some multiple will exceed 1. So then this sequence, so which is nothing but n alpha, n greater than or equal to 1, this is this sequence to infinity, and this is uniformly distributed. This is said to be let's write UD to stand for uniformly distributed. Uniformly distributed, we're going to write UD. Said to be UD. So uniformly distributed. Now we say that modulo 1, because we are looking at the fractional part. If the sequence of fractional parts so I'm going to denote fractional part by a curly bracket. So this is my sequence now. Okay, let's write it more precisely. So these are the elements of the sequence. Yeah. If the fractional parts, so that is inside 0, 1. It could be 0, but it's not 1. So that's perfectly fits inside this. So fractional part, the sequence of fractional parts is uniformly distributed. Is uniformly distributed in 0, 1. So that is what we defined first. So in this case, we are going to say that these are uniformly distributed modulo 1. So we can take any sequence of real numbers and talk about it. So the first example is the same, the n alpha. So n alpha is uniformly distributed. It is known that it is uniformly distributed for all alpha which are not rational. So for rationals, you can, if you just think a little, then you can figure out it's obviously not uniformly distributed. Because some multiples are, after some multiples, they will just be start becoming integers, and then it will just rotate, just a few finitely many entries, and then that will repeat. So that can't be uniformly distributed. Okay. And so because my focus is to talk about a finer property, something else. So I won't uh, I won't go ahead with more examples, but we would see some more examples which are coming from this concept of pair correlation, which I am now going to talk about. So uniform distribution is about an expected behavior. So if the sequence is uniformly distributed, then the number of elements falling inside a larger interval is more. So it's like a possibility, it's like a probability. So if you take a bigger interval, you get more elements, and that bigness is just a proportion of the length of the subinterval you are looking at. So a smaller interval get a smaller share, and a bigger interval gets a bigger share. That's the kind of thing happens. And let's just go to the next concept. Before that, I would just require a notation. So let me just make sure that we have the same notation in mind. So given a real number, x, so the curly bracket x is going to denote the fractional part. So this is going to be fractional part. Fractional part. So x is an integer plus a small thing less than 1. That is the fractional part. So fractional part is also x, and then when you subtract the floor of x, that's the largest integer less than x. So subtract it from x, then you get the fractional. So that's the fractional part. And so fractional part can take value between 0 and 1 with 0 closed, and for an integer, fractional part is 0 and 1 open. So this is the kind of interval we are looking at. The other thing is the distance from nearest integer, so which I am going to denote by double modulus, like a norm. So this is the distance for any real number x. So this is the distance from nearest integer. Integer, and this is going to take value between 0 and half with both sides closed, because it can take 0. Of course, if it is an integer, then it's 0, and it can be just halfway between, like 0.5, 1.5, then it is just half, exactly half. So it's a closed 0 half interval. So these are the two things we should keep in mind. I would use them in the definition. So our important definition is the following. So let xn be a sequence, again inside 0, 1. Oh, sorry, it is n greater than 1. Be a sequence of reals, of course, in 0, 1. So we define this quantity. We are calling it for any s greater than 0, any real number, any positive real number, positive non-zero real number. Define this quantity R. Let's stick to a. Okay, let's write S, N, and Xn. The sequence. This is the number of elements. First of all, it is the number of elements. 1 less than equal to. I'm going to explain this, so this is not easy to get. So this is the number of tuples of integer m and n up to capital N such that I look at the distance between xn and xm and look at the distance from the nearest integer. So I subtract xn from xm and then look at the distance of that number from the nearest integer. So we look at with this norm, and this is less than equal to s by n. So this is what the set is, and also we divide by 1 over n. So that's the quantity I am finding. And let me add a page. Let's see what this quantity is. So I have these pairs xn xm. So xn xm. So I have these pairs. I'm looking at pairs of numbers with m not equal to n, and we are generally going to assume that they are distinct. So m not equal to n, and then we look at this xn minus xm and let's suppose that falls inside inside 0, 1. Suppose it may not. It might be a bit negative as well. That's possible. So suppose it is inside. So let's suppose that would make it easy to understand. Let's draw that. So let this be 0 and this be 1. Now if it falls inside 0, 1, then what I am asking, if it falls inside 0, 1, then it might so happen that it is close to, it might be close to 0 or it might be close to 1. And in both cases, it can satisfy this condition. So what I am saying is that it should fall inside this 1 minus s by n. So it should fall in either in this interval, this part, or in this part of equal length. So that is s by n. So the distance, if it is inside 0, 1, it may need not be. It can be a bit negative. So that we would that is similar actually. So but it's easier to think, because if it falls between 0, 1, then we are expecting it to fall. We are not expecting. We are counting the pairs such that the difference falls inside either this interval or that interval. So these are the pairs we are counting. These are the pairs we are counting. And now what should we expect? So what should we expect? So the combined length of the interval is twice of s by n, because one of them is, so this is s by n and this is s by n, so it is twice of s by n. So that's the length of the interval. And how many things we have? Number of pairs. So number of pairs. So number of pairs are going to be n into n minus 1. Okay? Because we don't want to count the same one twice. So m is not equal to n. So therefore number of pair is n into n minus 1. But that is roughly n square. So if n is large, then it is n square, roughly n square, if n is large. So now what we want is to say that this number, so just thinking like what we did in uniform distribution, this is n. This is inside S by n. So this should be the number of elements, number of pairs into the length of the interval. This should be roughly equal to it. I really can't say that they are equal, so they are roughly equal to the length of the interval. So this is what we would expect. We expect this. So that will be an uniform behavior, just like in uniform distribution. So if it is number of pairs into the length of the interval. So how much is that? So number of pair is roughly n square, and length of the interval is 2s by n, giving us n times 2s, or rather 2s n. 2s. Now if I divide by n, so divide both sides by n, so curly brackets 1 less than equal to m less than, such that, so these are the pairs you are counting. This is the property. And so expected value, we can say that this is, so we have divided both sides by n, so it should be like 2s. And what we wrote on the left side, so what we wrote on the left, so this is exactly what we defined earlier as Rs n xn. So this is exactly the R of S in xn. So this is what we defined to be R in xn, which we have just seen. So what we expect is this should be like 2s, and that if that happens, if that expectation is satisfied, then we call that the sequence is uniformly, sequence has Poissonian pair correlation. So let me write that as a definition. So definition. So xn is said to have pair correlation. Yeah, so let's say just pair correlation. It's called Poissonian pair correlation. We just say pair correlation. Said to have pair correlation if this quantity, which we call Rs in xn, should converge to 2s for all s. Okay, so as of course as n tends to infinity, for all s greater than 0. So if this happens, we say that the sequence is pair correlation. Sequence have pair correlation. So this is an expected property. This is an expected property, just like uniform distribution. Uniform distribution is also a very intuitive property that we could expect. But not everything is uniformly distributed. Same is here. Now the point is, it might look that every uniformly distributed sequence is quite nice, and they should be nice enough to have this pair correlation property as well. Anyway, conceptually we are doing the same thing. We are looking at the pairs, and instead of the single entries, we are looking at the pairs and then looking at their differences, and if the difference falls inside an interval, we are counting them. We are just looking at the number of differences which falls inside them. So it seems that it might seem that it's very much similar to uniform distribution, and therefore whatever is uniformly distributed should have this pair correlation property, and vice versa. But that turns out not to be the case. In fact, pair correlation is a much stronger property than uniform distribution. So what is known is the following, that pair correlation it implies uniform distribution. So if a sequence has pair correlation property, then it is uniformly distributed. But the other direction is not true. UD is not necessarily pair correlated. The same pair correlated. In fact, it is known that in alpha is or does not have pair correlation for any alpha, any real alpha, never has pair. So then what does have pair correlation? So that's actually quite difficult. Any example turns out to be difficult. So there are certain exceptions. For example, this is known that if you look at square root of n, and then of course look at the fractional part, this has, okay, let's abbreviate this by PC. I'm calling PC, or even yeah, okay, this has PC. So this is pair. This has pair correlation. This is known. It's a non-trivial result, and it is expected that. So I should write that as well. Expected that n alpha, n square alpha, so I can just write the sequence like this. So with the understanding that we are looking at the fractional parts. So whenever I write a sequence of the reals, we look at the fractional part and then talk about this part. So it is expected that this has pair correlation for most alpha. For most alpha, under certain condition. Of course, you cannot expect it for a rational alpha because it's not even uniformly distributed, and we have already seen that pair correlation implies uniform distributions. Therefore, if we are trying to find examples of sequences which has pair correlation, we should first check whether whether it is uniformly distributed or not. And unless it is uniformly distributed, it doesn't have a chance to have this property. So as I've said that the examples are hard to find, but there is something interesting about this sequence n square alpha, which I would just say, let me add a page. And but what is known is this sequence n square alpha and as I said repeatedly, we would always be looking at the sequence of fractional parts whenever I'm looking at a sequence of general reals. So it is known that this sequence has pair correlation for almost all alpha. So for almost all alpha in the Lebesgue sense. So almost all in almost all in Lebesgue measure. Which is to say that the set of reals alpha which does not have this property has measure 0. So if you collect all the alphas such that n square alpha does not have PPC, then that set is going to have measure 0. So that is known. And so these are the kind of results that is known. So this almost all results. It's very difficult to pinpoint alpha. So it's worth looking at this kind of results for other sequences as well. And that is what we are going to do. So we have a definition. So definition. So let AN be an increasing, strictly increasing sequence. By increasing, I mean strictly increasing. Sequence of integers and so and this sequence is said to have metric Poissonian property, Poissonian correlation, pair correlation. I'm just calling metric pair correlation. Said to have, don't have enough space here. Just move this. Said to have metric pair correlation if AN alpha has pair correlation for almost all alpha. Again, in the sense of Lebesgue measure. Almost all real. And this we are going to write it as an abbreviation. So we just abbreviate this by MPC. So metric pair correlation, we just call MPC. So already I just said that n square. So that's an example. So this is the first example, that this sequence of squares. So these are squares of natural numbers. This has MPC. So this is what I just said, that n square alpha has pair correlation for almost all alpha. Therefore, you can say this using this definition, following this definition. Now let's look at how does one approach such a problem. So that is what I want to talk about. Let me start by this. So suppose I have this sequence xn or this an alpha and so I would like to calculate this number, that S n an alpha. So this is 1 over n. Just recall this. So an minus am, we can write it like this, and into alpha. The distance from the nearest integer, this should be s by n. That's the number. So this is what we want to calculate, and I want to say that so this goes to 2s as so this is just to recall. So P is pair correlated. This is pair correlated if this happens. If this happens.
Anirban,
yeah.
So do we know any irrational alpha for which?
Yes, exactly. So there's a precise example. Yeah, there were some examples known. There were some examples known. But possibly with, I mean, no pinpointed alpha, some kind of properties of, so there is a list of property, if it satisfies this and then it happens. This kind of result is not.
Okay, but no explicit example.
No explicit example. Yeah, no explicit example.
Okay. And another thing that the sequence n doesn't have MPC, right?
No. Yeah.
Okay.
Yes, exactly. So that is an example. Yeah, I should actually write that. So this is a sequence which has MPC, and this is a sequence which does not have MPC. Yes. Yeah, so what I was just recalling is the definition of this counting function, and we expect these to go to 2s as capital N tends to infinity, and that should happen for all s greater than 0, all real numbers. And we want to prove that this kind of thing happens for almost all alpha. First of all, let's just frame this. So to frame this, we are going to introduce a characteristic function. So define this characteristic function. So phi s by n, s by n, say, let's write it. So this is a function on 0, 1. So it's a characteristic function. So it's going to take value only 0 and 1. You can just think of it as a real function, but it's going to take value 0 and 1. So what is this function? So x by n let's write t. This is going to be 1 if the distance from nearest integer is s by n and 0 otherwise. So that's the point. So therefore, R. Okay, let's use another notation as well. So a new notation, just to write it, make it a bit smaller, easier to write. So notation R S N alpha. Let's write like this. So this stands for. I'm just dropping that A. Since we want to prove this this kind of convergence for almost all alpha, so we need to consider this RS in alpha as a function of alpha. That's the thing we are doing. S is going to be fixed and looking at it as a function of alpha. Yeah, so that's just a notation. And now if I write this in terms of this characteristic function, so we have R S in alpha is 1 over n, then the counting. So counting is just now 1 is less, just counting. I can write it in terms of the characteristic function. So chi of s by n a n alpha by a n. So I can write it. Or in a slightly nicer way, I can just subtract and write a n minus a n into alpha. So this is what it is. Now what we have, we can also write a Fourier expansion for this function. So I would use the notation. So use this kind of write it like this. So there is a bit of a thing to be, bit of a clarification to be given. So CR are the Fourier coefficient, then E of Rx, so this exponential function, it's usual Fourier expansion, and but this equality is questionable. I would just explain it. Let me just write down the notation first. So E of Z is exponential E of 2 pi I Z. So these are my exponential function. This is just to write the Fourier series in an easier way. So how can I write that? Because this s by n is a function on 0, 1, and which we are identifying with R mod z, and therefore it has a Fourier series expansion. It's a periodic function, and it has a Fourier series expansion, and its dual space is Z, so it's a series. So it is series, and CR are the Fourier coefficients. So CR are given by CR is given by the integral 0 to 1 of this. Okay, let me write CR more clear. Let me just add it. CR is going to be 0, 1, or you can, this is an integral over R mod Z actually. You can write 0 to 1, you can write R mod Z, it's the same. And the function is by n, say t, e of minus r t. So this is the Fourier transform, and we have the Fourier series. Now this is this. Why is this equal? So this is not an equality of functions on R mod Z. This equality is in L2 space. So this is an equality in L2. So in square integral function. So this is in L2. It's not a regular equality. So I would in fact replace this equality by a tilde, because it's not just an equal function. It's an equality only in L2. Anyway, don't bother much about that. If it is not clear to you, it really doesn't matter when we go ahead. Just remember that there is it's not a regular equality of functions on R mod. But I mean, as far as the calculation is concerned, it's not going to matter much because we are going to look at the variance. So what is the variance, you might say? So what we would do, so let me just calculate this. One second. So if you see that the 0th Fourier coefficient, is going to be 0 to 1, and then chi s by n t dt. So no exponential because r is 0, so that has become 1. And this is just exactly the length of the interval, so 2s by n. And we suppose that n is much larger than 2s, so there is no problem of wrapping around 1. So this is with the assumption that s is, because s is fixed and n we want to take it to infinity, so s is small, much smaller. And this is what the expected value is. So of course multiplied by n, that will come when you just do the count. So one second. So if I now integrate r alpha s, okay, let me just, sorry, s n s in alpha d alpha. So this is going to be, this is the expectation. So I am thinking of this function r s n alpha. S is fixed and it's a function of alpha. We are considering it as a function of alpha and then integrating over r mod z or 0, 1, whatever you say. So that's going to be that's exactly going to be n into n minus 1 by n square and 2s. So it's going to be exactly like this. So if you do the integral. So that's roughly 2s. So that is roughly 2s. So we want actually the expected value. That's the main thing. And we are now going to look at the variance. So what is the variance? Variance, look at the function. So as I said that this is now thought of as a function of alpha. And alpha is running over 0, 1 or R mod z, which has been identified with R mod z. So this minus 2s, which is the expected value, so that's the expectation, or to be very precise, you can keep this written. So if you cancel n, then this is n minus 1 by n into 2s. So that's the precise. And look at this, square it, and then integrate 0 to 1. And what we want to prove is something like this. That we want to prove that this is sum into the minus theta, or even better, let's say we want to prove something like this. So this is what we want to prove. And then by applying, if we can do this, then by applying the Borel-Cantelli lemma, we can show that this AN alpha has Poissonian correlation for almost all alpha. Now the use of Borel-Cantelli lemma is not, and concluding it it's not very straightforward. It's a bit technical, because what will happen that you are going to save only a little power, a very small power, and therefore, so let's if I write this variance as, say, Vn alpha, because that's what matters. Alpha, no, sorry, alpha we have integrated. There is no alpha. Sorry. So this I should write it as Sn. And at that point, n is more important. N is the value. So B alpha. So what we would to apply Borel-Cantelli, what we would like is the summation Vsn to converge. So this we would like to convert, but that will not happen if we have a very small power. If we have a very small power of small negative power of n, that series may not converge. So what we would have, what we need to do, we need to pass to a subsequence. We take a subsequence where the convergence becomes fast enough to get this series convergent, and then use Borel-Cantelli, and then we have to sort of use a sandwiching argument to conclude this result for the full sequence. So that's a bit technical thing. I'm not going to be able to talk about that. So just a very brief flavor of the argument. But what I would like to talk about, I have very little time left actually. Okay, let me just think what I should talk about. So in fact, this when you calculate the variance, you get a very interesting sum. Let me, since I have very short, little bit of time, so I'll talk about a very interesting sum that you get. So by calculating the variance, you end up getting a sum like this. While variance, you get a sum of this form that let me just write it. So V and W are variables running over non-zero integers. I would just explain what this notation is. Rn of P, Rn of W, and then I have WV, the GCD, the square root of the absolute value of the product. And these things, which I can just write, this is the number of way you can write W as a difference of this AN and AM. Let me write. Such that AN minus AM is equal to B. So AN is the sequence we are working with. That's strictly increasing. So AN and AM are not going to be equal because their indexes are not equal. So that's going to be non-zero, and we are summing over non-zero. So that makes sense. So these are these kind of representation functions. So these are number of ways you can write an integer in terms of differences of the original sequence, original integer sequence you start with. And this is the GCD. So this is the GCD. And since we are also looking at negative integers, so we take the absolute value of the product before using the square. So these are very interesting sums. These are called GCD sums. So GCD sums, and there is an interesting literature and a lot of work on these GCD sums. This connects to Riemann zeta function actually, and a very interesting thing happens in this. So these are GCD sums. So it need not be need not have this representation function. You can write it in general that just for some real numbers, sorry, integers, sum over integers, non-zero integers because you are going to put product, and some function non-integers. So if A, if B, if you wish, you can have complex value function as well, so that you use a conjugate, and then the GCD A comma B. So usually it's considered with this, that 2 alpha and then product AB with alpha. So alpha is greater than 0. But of course, convergence etc. is a question. So you can define like this. So to handle the convergence, you would generally assume that if from Z to complex numbers has finite sum, then it's just a finite sum, which is the case here. Finite sum. So these are just finite sums, which is well defined. And finding various estimates on these kind of things. That's the topic of GCD sum. So one last small comment. So what we would finally get if we compute this thing is, so much of the thing is going to depend on the L2 norm of this Rn, the representation function. Let me just see, it's actually not so heavy thing to understand, it's quite easy. So what we would get is this, let's change the file. Let's change this Rn. So we are finally going to get this kind of thing. We sum over V and square of this. So that's what I call P2 norm. And these are finite sums because not everything is going to be represented. We are looking at only finitely many differences. So yeah, so just remember that these are going to be finite sums because we are just looking at ANs for small n up to capital N. Small n and m are up to capital N, so we just have finitely many elements. So it just represents finitely many elements. And this is what we are going to look at, and this is going to be exactly same as this quantity, that m, n, k, l, all integers, such that so they are all integers between say 1 and n. So this is in all are 1 and n, and such that am minus an equal to ak minus an. So this is a very arithmetically interesting set, and this cardinality is called the additive energy of the sequence A. So all these things connect together. Actually, we started with something else, but this comes to this kind of a combinatorial object as well via this GCD. So okay, so I'll just stop here. I actually have taken more than the allotted time. So yeah, questions are welcome.
Yeah, before going to the question session, I request everybody to thank Professor Anirban Mukhopadhyay for his wonderful talk.
Thank you, sir.
Any questions?
Sir.
There is something in the chat box. No, this is. Oh yeah, this is a good question actually. That whether 2s is less than n. Yes, so I mean I probably have already answered. So since you are going to take n to infinity and keeping x fixed, so n is going to eventually exceed. So looking at s which are much smaller than n.
Any other questions?
I had this question related to GCD sums. So if we take this both functions f, I mean this function f to be identity, is there some realization on the bounds?
Okay,
Like,
just 1 second. I'll just I can't hear it. So 1 second. I'll just.
So Siam network is bad in France too, is it?
Yeah.
Yes, and the residence is quite bad.
Yeah, no, go ahead. Yeah.
So if we take this function f in the GCD sums in the GCD sum to be identity, and we bound A and B by some, like, just take up to some n. Is there some realization on the bound of this sum? Like,
yes, so you are going to take just one, right?
yeah.
This f function is just identity.
Yeah.
Yeah, there is a, I mean, quite a bit of literature. In fact, there are results by Tenenbaum and De La British. They have a new result, and there are lots of work by this Bondarenko and Sai.
Okay.
Yeah. So if you want, I can give you the references.
Okay, sir. Thanks.
Just send me an email. Whoever is interested in more references, etc., then just can send me an email.
Okay, sir. Understand.
Any other questions? Okay, if there are no other questions, let's thank Anirban sir once again.
Thank you. Thank you.
Yeah, thank you, sir.
Thank you, Anirban.
Yeah. Okay. Bye. Bye then. Bye. Yeah. Thank you.